Good evening, everyone. For this session on competitive programming series. Okay, so we are doing it specifically for Algoqueen, and we are covering a range of topics under that. Myself, Swaminathan J. I am an associate professor in Amrita Vishwa Vidyapeetham, and actually I lead this Code at Amrita Club. So where we have a bunch of students, and then who are interested in this competitive programming, and then we do that. Just a second. Okay, so let me just quickly start the presentation. I hope you are able to see the screen, right?
Yes, sir.
Okay, so this is the agenda. Okay, so we will do what is warm up on what is meant by computational complexity, because this is a one important thing when you want to. So whenever you program, you have to be worried about the complexity, right? No, you don't want to do some program which is very inefficient, right? So the complexity, computational complexity says that now how much it is, your program is spending time, right? So that is the thing that we have. So basically, this is what computational complexity is about. Then we have to mesh. Then we talk about what is meant by running time. How do we measure it? And then counting, like now, what is the strategy that you use to measure the running time? And then what do we mean by time complexity? Actually, this is a little bit of an involved topic, okay? But no, we will do it in a more simplified way, okay? Because this itself may take about like 3 or 4 lectures. So I'm just trying to condense it so that we get the idea of what is meant by this time complexity. What do you mean by the big O notations, and then when you say order of n order of n square, what do they mean? So that's what we will look about. Okay, and then we'll also take an example and see how this really matters when it comes to submission of a solution for a given problem. Okay. So let me just start with some kind of a warm up. You can answer this question. So these are the you see there are 2 programs here, right? So which program runs faster? The left one or the right one? Anybody can answer, or it doesn't matter? Nija, can they answer? Are they allowed to answer? Do they have a?
Yes, students, you may please raise your hands if you have the answer. Yeah.
Okay.
Yeah, Tamil Selvan, you can talk now. You can just unmute yourself and then talk.
Yeah, please go ahead.
There is no yeah. No, sir, there is no response. Anyone else have the answer? You can just raise your hands. I will just unmute yours. No, sir.
Okay, fine. Let's go ahead. Okay. So apparently it looks like now we are using 2 output statements here. There is only 1 output statement. Okay. So probably we might think that this is going to take more time than this one. But really you cannot say, because these are just 2 instructions. Okay. So how slow it will be, the second program or the right one will be compared to the first one. It may not be noticeable at all. Okay. So we'll not be able to say just by looking at it, and then I think you might have guessed. So sometimes it can so happen that the right program can run faster even than the left program. Now, if in case when you run the left one, there is a there is a heavy application like a video application or some other application running in the background. This could slow down the other machine. As you know, computers are multitasking machine, right? It is simultaneously doing multiple tasks. So when it is running your program, it may be doing something else. And when you're running this particular program, it will be doing some intensive CPU intensive task or whatever. So because of which it may take more time for the left program to run than this. Okay. So, and because now the instructions are very less comparatively difference, so you really cannot say that. How about these two programs? Is there somebody ready to answer? So which one will run faster? Look at this and then tell me which one will run faster. The problem is about computing the sum of first n numbers given n. Anybody willing to answer?
Okay. No, sir.
Okay, fine. Let's go ahead. Okay. So it would have been good if it was interactive, but that's fine. No problem. So if you look at here, if you take this, whatever n you give here, now it's going to take almost the same time because you are doing one multiplication, one addition, and one division, right? That's all you are doing here. Okay. So no matter what your n is 100 or 500, it doesn't really matter. But in this case, it's going to matter because you're going to loop as many number of times, right? So n is going to matter. So if somebody asks you, is the left one faster than the right one, you will surely say it is S. Okay. And the right one takes one more point. Notice the right one takes varying time, right? Depending upon what is the size n. Okay. N is the input size, and depending upon the size of n, it may take more. So if it is 1,000, it may take certain time. If n was 10,000, it may take some more time, right? So that is what, because now you're going to run in the loop, and then now you're going to do so many number of additions and then so many number of assignments, right? So that many number of times you're going to do, and finally you're going to return the sum. Okay. So obviously the first program is more efficient than the second program. Okay. So when we want to say this in a very quantified terms, that's why we introduce the concept of time complexity. Okay. So how do we measure the running time of an algorithm? Just let's take a look at it. So what we can do, given an algorithm, what I will do, I'll go and code the program, okay, in a particular programming language. Whichever language I know or whatever I prefer, I can code it in a language, run it on a machine, and note down how much time it takes for my program to run. Okay, so then I can say this algorithm takes so much of time, like 15 milliseconds, or 500 microseconds or something like that. Okay, so I can do that. Okay, so the question is this a reasonable strategy? Okay, is this a reasonable strategy? If you have an answer, probably if you can again answer. I think Nija, I think considering that there are only very few participants, perhaps we can open um, the audio for everyone, right? So in case they have any questions, they can answers, they can say it.
Sure, sir. I'll just unmute.
If there is disturbance, then we can go back, right? So
okay, sure.
Does this sound like a reasonable strategy? That given an algorithm, code it in a programming language, run it on a machine, take the note of the time taken, and then say this is the running time of an algorithm, right? So, what is your opinion? I'll count from 1 to 5. Now, if you have anything, you can answer. 1, 2, 3, 4, 5. Okay, so nobody's answering. So let me go ahead. Okay, this doesn't sound like a reasonable strategy because the question comes, okay, what is the programming language that you're talking about? Because different programming languages takes different time. For example, and then there is one more question, like now, what is the machine configuration? You are saying you run it on a machine. What is the machine configuration? Is it like the latest high-end machine, or is it a regular machine? Is it like an i3 machine or i7 or probably even a mainframe? What a machine that are you talking about? Because it can vary with one machine to other, right? So in a faster machine, the same program will take lesser time, right? So this is a very basic fact. And the other thing is, will the program take the same time to run always? Even though you run it on the same machine, no, this is going to take the same time always. No, not necessarily. So probably at the microsecond level or the nanosecond level, there can be some difference, right? So what would you take it as a um, real running time, right? If you have multiple running times, what will you take it as a real running time? So that's a fundamental question. So if you take C plus C, C plus plus, they run faster than Java, which runs faster than Python, right? So if you are implementing the program in let's say Python, you will get one measure of time, and if you run it, do it in C or C plus plus, you will get another measure of time. What would you take it as a running time? Okay. So that's a question. So this is not a, this doesn't seem to be a very straightforward thing. Okay. So then the hardware also, you can say today you can measure with the best hardware and then say this is the running time of an algorithm. But then, 5 years from now, you will have some machines which are much, much faster than this because the hardware speed has been increasing like anything, right? So they keep getting better and better, and there are different kinds of hardware. So which hardware you will take it as the standard and say, so decide now what is the time taken. Okay. So again, this also seems to be like very varying, and we can't rely on, right? And finally, each run takes a different time even on the same machine. That's a real fact. You can run the same program multiple times and then really see what is the, so we really don't know what is the correct time, right? So the same machine, same program, but different times you will get. Okay. So this doesn't seem to be a reasonable strategy at all to measure the running time of an algorithm. So what do we do? How do we measure the running time? Okay. So the suggestion is like, don't go for computing the running time based on the time taken on a given mission for your program to run. Don't do that. Okay. Instead, count the number of basic operations that you execute. Okay. So what do we mean by basic operation? It will be obvious. I'll just get into it. So basically, assignment, addition, subtraction, multiplication, comparison. These are all some basic operations that we do. So if you take a program and count how many such operations that we do, like a return, like a function call or whatever, right? So you do count that number of basic operations, and once you count them, then you say, okay, this many basic operations it takes. So that's running time is that. So now, the advantage of this approach is that no matter which machine you run, okay, no matter which programming language you write the program on, okay, no matter how many times you run, the number of instructions or the number of basic operations given an algorithm remains the same. Okay, so therefore, this is a more standard measure to find the running time. Okay, so running time, as per our analysis, is not really the time taken, is actually the number of instructions or the number of basic operations that are executed, okay, that are contained in the program. Okay, so that's the thing. Okay, so let me just go into it. So we are going to say count the number of basic operations and then we will see. Okay, so let's take a program and then see what is the running time by counting the number of basic operations. Okay, so I'm going to take an example of linear search simply because many of you or most of you would be familiar with such a search, and it is easy to relate. Okay, that's the only thing. Okay, it's a simple problem, but no, it has some profoundness associated. Okay, so like in a linear search problem, what do you have? You're given an array or a list. So and then you are also given a key. Okay, and you are looking for the key in this particular array. That means you're searching for the key in this particular array. So basically saying that, does this element exist in the array? That is what you are looking for. Okay, so so in an array you can index the positions, right? So 0, 1, 2 and all that. So if the array name is a, you say a0, a1, a2, all the way till an-1, given the size as an, right? So that is the thing. Okay, so for what you will do, you will first look for a key in the 0th position. Now, if it is matches, then you are done with it. Okay. Otherwise, you will start going rightwards and say, is the key present in the next position, all the way till the end. And by the time you complete the entire thing and you didn't find, then you will say, no, false. I couldn't get it. But if it was in some position, you can say, yeah, I found it. Right. So your answer is a yes or no. Whether I can get the key, is the key present in the array or not? So that is the essential problem, right? So let me give you an algorithm here. The algorithm is like this. So just to see that it's the input is array of size n and the key, and you're looking for the key in that array. Okay, so your output is either true or false. If key was found in any position of the array, then you will return true. Otherwise, you will return false. Okay, so now the code. Let's come to the code. Okay, so you are not declaring a variable found and which is initialized to false, right? What it means is, have I found it yet? Have I found key yet? present in the A. Okay. Before we start, we have not found, right? So therefore we would say it is false. Okay. Then what we do, we just go through the entire array from 0 to n, just watch, and then if at all it matches, if key matches the array index, then I'm saying found equal to true. That means I'm successful in finding, therefore I will set it to true. So, and then, sorry, I think here it should be, I'm going to return found. Okay. I'm sorry about it. So basically, now you have the program where you'll say found. Okay. If it was not found in any position, then found will remain to be false. Therefore, I will return false. Otherwise, what I will do, I will return, true, because found will be reset to true at any point of time. So that's basically the idea here. And therefore, what do? Now we go through this search. Now let's say, let's count the number of basic operations. We said basic operations, right? So let's count the number of basic operations. So here we are doing one assignment. That means one basic operation that we are doing. OP represents operation, basic operation. So one assignment operation. Let's come to here. Okay, let's quickly go through. I equal to 0 is done only once. Therefore, one assignment is done. And then you are comparing I less than n. Right? So the 0 value will keep going from 0, 1, 2, 3, 4, all the way till n. So typically you would do n comparisons, right? So because you are executing this n number of times, okay? And then you are incrementing it n times again, I plus plus. From 0, it will get all the way to the value n, right? So it is going to keep getting incremented. So there are n increments, n comparisons, and then one assignment. So therefore, how many number of operations you do? You typically do 2n plus 1 operations here. Okay. So how many times you are going to do this comparison operation, key equal to AI or not? Okay. Whether key is present in a particular position or not. How many times you would do? You would do n times, right? Because this is the size, right? So you'll be checking this, okay, whether it is found or not. Okay. And if it was found, then you will reset found to be true. Okay. And this you can do anywhere between 1 to n times. In fact, it is 0 to n times. Okay. Because if I don't find it key in any position, it would be 0. If I found it in some the first 0th position, that is this location, then I would do it once, twice. I mean, if depending upon the multiple locations it was present, if it was a duplicate item, or it is present in multiple locations, I'd be doing the setting found to be true again and again. And mind you, this is not the most efficient algorithm, but anyway, this is the algorithm. And then finally, once you are done with it, then your found will contain really the correct value. So the return operation will take one operation. Okay, one operation. So this is what we mean by basic operation: assignment, comparisons, increments, return, these kind of steps, or a function call. These are the steps. So basic operations. So we count so many basic operations. So in this case, if we count, now at the most it will be something like 4n plus 3. I add up all this stuff, then I'll get 4n plus 3. At the worst case, okay, the worst case. So now we can say what is the running time. So I can say that running time is, if your input size is n, then it's going to take 4n plus 3. Okay. So that means that many number of basic operations I'm going to do. No matter which machine you run, no matter which programming language you use, it is going to be this much. Okay. So therefore, this becomes language independent, hardware independent, platform independent, and then execution independent, right? So basically, just by looking at it, by calculating this, you'll be able to. And one more thing is, we'll always take the worst case that is used for characterizing any algorithm, right? But when I say running time, we'll say what is the worst case running time. That means sometimes what can happen is you might have an efficient algorithm. Let's say in this case, if I found the A to be, I mean the key to be there in any location, and let's say it was in the first position, I can set found to be true and then return found immediately and get out of this, because I don't have to keep searching for it, because all I'm interested in whether it is present or not. If it was present, I could stop right here. If it was present here, I could stop right here because I found it, right? So I really don't need to loop around so many number of times if I really found it. So therefore, the best case, in this, if you want to run, then it would be something like, if it was found at any position, return found to be true and then get out. Okay. don't go again and then search for the rest of the array, because it's not even necessary, right? You achieved your task and that's it, done. So go ahead. So if you had implemented that way also, um, even then, no, we will always consider the worst case time, because you never know where whether your key is there or not, which location it is. So we can't make assumptions saying that no, key will be found in the first location or first half of the location. We cannot make any such assumption. So what we'll do is, in the worst case, I may not find the key, or I may find the key at the last position, in which case I'll be doing so many things. Right? So that's what counts. Okay. So you would take that many numbers. So the worst case running time is what you would take. Another aspect that we look at is, we sort of assume that when you say 4n plus 3, so we assume that now all kinds of operations will take the same time, but it's not really the same, because some kind of a memory bound operation will take, the increment may take lesser time. Okay, assignment will take more time because it involves two memory locations, right? So you have not just memory location, and then you have to set something to it. So at most, so this can take more time, right? And suppose storing any memory kind of operation will take more time. But any CPU bound operation, like for example, you are doing incrementation, you are doing multiplication, division, these kind of operations will take lesser time, right? Because it's done in the CPU. But if you're shuttle between CPU and memory, then it's going to take more time. So, but no, as per this strategy that what we are doing, we are always assuming that the operations almost take the same time, because we are just adding, counting together and then adding up, right? So, but what if assignment takes 10 times more time than the increment operation? Okay, then this 4n plus 3 is not true, right? But we are not really worried about at that level. Okay, and the reason for it I will just tell you in the next slide. So let me. So when you come to it, let's just. So you have this linear search algorithm. So what we will do is, do we really need to say it's 4n plus 3? How many times? How many operations and all? Then if you literally investigate, it's not really necessary for you to go through all that stuff, right? Because the n is what matters. So as n gets larger and larger, you will be looping around so many number of times. Okay, and then you will do 4n plus 3. So what is 4 and 3? 4 and 3 are constants. Okay, they may not have that much of influence than n, because it's the n which is the varying factor. So consider only n, and then what is this n? Basically, it is actually number of times you're looping around, right? So in this case, for I equal to 0, I less than 1, I plus plus. So it's going to take the value 0, 1, 2, 3, 4, all the way till n minus 1, or till n. Okay, it's going to take all these values. So therefore, no, we can simply say the time complexity is order of n. That's it. Okay, the time complexity, because this is the number of times you loop around. Okay, so forgetting what you do inside there, and then this is the one which is going to matter when n is really very large. So I given some examples. You can look at it. Uh, so suppose if you say if there is a loop like this, for I equal to 0, I less than 1, I plus plus. So it's like that. Then you typically run this. I would take value from 0 to n. Therefore, roughly n times. It's going to be n plus 1, but roughly n times. Then you will say no, that running time is order of n. Okay. This is what we mean by time complexity. Okay. Time complexity, we don't say 4n plus 3, or in general an plus b, or an square plus bn plus c. We don't say like that. Okay, we take out all these things, and then we say it's just a n matters. Okay, so how many times you are looping, it's going to be n. What if you had a loop like this, for I equal to 0, I less than 1, instead of I plus plus, I'm giving I plus equal to 2. That means you are incrementing twice. If I was 0, the next I value will be 2, 4, 6, 8. So like that. Okay, and soon you will get to n, right? So your values will be 0 to 4 all the way till going till n. Okay, so n by 2 times. Okay, then what you say is n by 2, no big deal, because it's only a constant. You strike it off and then say still it's order of n time. Okay, the constants you just don't give any what do you call, any importance. Okay, take an example like this. For I equal to 0, I less than 1, I in I is equal to I into 2. So that means no, initially it's actually no, I should start from 1. It should not be from 0. I should be starting from 1, because if I start from 0, I into 2 will always be remaining 0. So let me just start with 1. Okay. These are all some minor things. Okay, so the thing is, so here it will be 1, it will be 2, it will be 4, it will be 8, like that it will be going on. So sooner you will get. So basically, if you look at it, this would take about log n time, right? Because you are quickly going to it. So if n was 16, then I'll say 1, 2, 4, 8, 16. Okay, so by 4 jumps, I'm reaching it, right? So what is 4? It is log 16. Okay, given any n, and then it's going to take so much time because you are going very fast. So that's why this, now you'll say time complexity is order of n, right? Order of log n. So you take a binary search, it is going to take order of log n, because you are going to do this every time your size becomes half and half. You might recall, like, what is it? Take this kind of a loop, a nested loop, for I going from 0 to n and j going from 0 to n. Okay, this is kind of a nested loop. So for I equal to 0, j will take all these values. For I equal to 1, j will take all these values. Finally, when I equal to minus 1, j will take all these values. So there is a n times, n into n times, right? So for every value of I, there is going to be n values of j. And how many values of I exist? There are n values. Therefore, it's going to be n into n order of n square, nested loop. And then again, you have like I equal to 0, but no, a similar thing. But I think, there is fundamentally no difference between these two. Okay, so we can leave it as it is. But now this is the way. And even I think I would have meant to put I here. I would have meant to put I here. So it will take only 0 value, then it will take 1, 0 and 1, then it will going to take all the way till I. Okay, so it's going to add up to 1 plus 2 plus all the way till this thing, which will actually result in order of n square. Okay, so because this is n into n, n into n plus 1 by 2, and therefore it's going to be n square. Okay. So what do we conclude from here? Okay, the conclusion is that, no, don't worry too much about constants. Don't worry too much about the lower order terms. Okay, so suppose if I give you two algorithms. Okay, this is the most important point. Okay, if you grasp it, then that's the takeaway point. Okay, if you have two algorithms, one algorithm is taking 2n plus 3 time running time, another algorithm is taking 5n minus 7 time. So you want to determine which is a better algorithm. Then what it says is, no, don't worry about all this. Okay, remove all these constants. Okay, then what will be the time complexity? It will be order of n, right? So both are linear. So you pick either one, it doesn't really matter, because it's a n that matters. It's a n that matters. Now let's take another case. So you had something like this, an algorithm which contains a nested loop, therefore it is n squared. Apart from that, it contained another for loop, so therefore it is n. And then you had only one nested loop here, n squared. But again, no, you can cancel all the constant terms. You can also cancel the lower order term, because lower order term will get masked because of the higher order term. Okay, the way n square is going to grow is not the way n is going to grow. So this is going to overshadow this n. Okay, so therefore, no, it doesn't really matter. As n keeps increasing, it's the n square that matters, not the n. So then you will say both are quadratic, so take either one. It doesn't really matter. Okay. Then if you had two things like this, one algorithm is taking 2 power n time, that is exponential time. Another algorithm is taking n square time, which is quadratic, or we can say polynomial. So then what will you choose? You would choose n square. Okay, because that's going to be faster algorithm, right? Because n square grows slower compared to 2 power n, right? So if n is 100, n square will be something 10,000. 2 power n will be some number which is like too long a digit at all. Okay, so therefore, no, it's not going to. This algorithm is very inefficient, and this is the algorithm which is efficient. Okay, so typically, what you will do, you will say that if your two algorithms are there, one algorithm is taking n time, another algorithm is taking n square, you prefer n algorithm. Okay, between n square and n cube, you will prefer n square. So like that, now you have a series of range n power k all the way till the n, and when you have root n, that means is n power 0.5, n power half. So that is going to be a bed. So if you have an algorithm which takes root n time and another algorithm which takes n time, doing the same thing, you will prefer the root n algorithm because that can run fast. Okay. So that's basically the idea. That's how you will pick it. So these are all called as a polynomial kind of a, algorithm, right? So which takes n power k. Now, if you have something like n or linear, quadratic, cubic, or anything n power k, then you would say that they are all polynomial kind of a algorithm. It takes polynomial time. But you can also have like an exponential time, where it is the reverse, like 2 power n, 3 power n, all the way n factorial, n to the power of n. These are all numbers, which are actually going to be, they are going to grow faster than faster. Okay, so they are all exponential. So if you are given generally any polynomial algorithm and exponential algorithm, two algorithms, and ask which do you prefer, you will always prefer a polynomial, right? And then you can also take log, for example, binary search. Okay, it takes log and time. Okay, this grows much slower, so you will prefer logarithmic algorithm. Given a polynomial algorithm and the logarithmic algorithm, you will always prefer a logarithmic algorithm because it runs faster. Okay, because as n keeps increasing, log n will be smaller compared to n or n square or even root n. Okay, so and you can also have an algorithm which takes only constant time. For example, the sigma example I taken, if you compute by n into n plus 1 by 2, that's going to take always a constant time, right? So that you would prefer, right? So basically that's the idea. So now, having done this, let's just go and look at this particular problem. And we'll look at two algorithms. One will give, because of the efficiency or the complexity is higher, it will not get accepted in the sense the time limit exceeded you will get. Whereas the other modified algorithm will be able to solve the problem. So before going to Codeforce's website, I just want you to look at this problem and probably try this in your notepad. Okay, just try to make and understand this particular problem. Okay, I'll give you 2 or 3 minutes. You can just look at that. Then we'll go into Codeforces. I hope you are able to read the problem. I'll quickly do an explanation. Um, it says that no, it's a kind of a weird subtraction is involved. Okay, so you are given two variables which you call it as a and b, and you will do some operations on these variables. So what would you do is, if a and b, either of them is 0, okay, you will just end the process and print whatever values a and b have. Okay, so if not, then you will go to step 2. What does step 2 do? Um, if a was greater than 2 times b, greater than or equal to, then what will you do is you will reset a to be a minus 2 into b. Okay, so that's what you would do. And then repeat step 1. Okay, now we will just check whether a equal to 0, b equal to 0. That's what you will check. Okay, so that's all. Otherwise, go to step 3. So if a was not greater than or equal to 2 into b, okay, then you will go to step 3. What does step 3 does? It will check the reverse, right? If b is greater than 2 times a, if that is so, then set the value of b to b minus 2 into a. And then you will repeat step 1, right? Whether a equal to 0 or b equal to 0. That's what you will just check. Okay, and then but suppose b was even not even greater than or equal to 2a, you will just end the process, and what you will do is you will print that value of a and b. Okay, so to the extent these conditions are satisfied, either of these conditions are being satisfied, you will keep reducing the a value or b value, and finally when you can't do any more, okay, when a is not more than twice of b, or b is not more than twice of a, you will stop that. You'll stop the process and then finish it. Okay, and then you will print that a and b. Let's take this particular example. Sample input 12 and 5. Okay, a is 12, b is 5. Okay, um, now 12 is first of all, none of them are zeros, right? Both of them are not zeros. Okay, therefore the first thing is not, first condition is not true. Therefore, we'll go to step 2. What do we do in step 2? We check whether a is greater than or equal to 2 into b. So therefore, here you just check whether a is greater than or equal to 2 into b. Yes, it is, because 12 is greater than 2 times 5, right? So then what you do is a minus 2b is what you do, and you get the another a. So 12 minus 5 into 2, that is 10. You will get 2. So eventually you get what is, let me do it here. So this is, and the next step, it is going to become 2 comma 5, 2 5. Okay, a becomes 2, b becomes 5. Now in the next step, what happens? A is uh, then now you're coming here, right? B is greater than or equal to 2a. Now b is greater than or equal to 2a, because 2 times 2 is 4, which is less than 5. So therefore now you will apply the second logic. You will apply the second logic, and then you will say 5 minus 2 into 2, which is going to become 2, and then the value will become 1. 5 minus 2 into 2, that is 5 minus 4 equal to 1. So at this point of time, then now we are going to check again. You are done with it. Um, so now you look at it. See, it's 1, 2 times less than. So now again you are going to step 1. Step 1 says no, it is not possible. A or B should be equal to 0. Then come here whether 2 is a is greater than or equal to 2 times b. Whether 2 is greater than or equal to 2 times 1. Yes, it is true. At that point of time, you do 2 minus 2 will become 0. Therefore, it will become 0. And that's the answer. After this, you cannot proceed, because when you go and check in step 1, one of them becomes 0. At that time, you stop. Okay. So this is what you typically do here. Okay. And then you will get 0, 1, and your process stops, and then you will print them 0, 1. Okay. Similarly, if you take the sample input 30 on 12, so 31 minus 2 into 12 would be 24. So 31 minus 24 would be 7. Okay. And then at that point of time, you will stop, because you cannot proceed with this. You cannot proceed with this. Okay. So that time you will stop here. And then you have another example, 25, 49. So 25 into 2 is 50, and 50 is greater than 49. So none of the conditions hold. So therefore, no, you will not be able to do any of the reduction process or a subtraction process, and you will just print 25, 49 as it is. Okay. So this is the problem. Okay. So let's just go into this particular problem. Let me just click on this. So this is the problem that they have given, a weird subtraction. Okay, it's exactly the same problem. I put it in the slide, but exactly. But one thing that you have to observe is they are saying that the initial, they are saying n and m, it's actually a and b. Okay, so it's a mistake here. So m is the initial value of a, that's what they're saying, right? The initial value of a and b, which is like n and m, they can be anywhere between 1 and 10 power 18. 10 power 18 means it's a very, very large number. 1 followed by 18 zeros. Okay. So only a long can hold it. Okay. Such is the kind of this thing. So this is going to matter for us. Okay. So what you can do is you can code this. I've actually already done the coding, so which I will explain. So I have a Java code which I will try to explain. Fundamentally, it is pretty much the same. So let's go into this particular. Say they worked out this example also. the sample input, how you are getting 0 and 1. Okay, so that's what they are doing. And this is the problem. So let me just take a thing now where it is saying time limit exceed. Okay, so let's click on this particular thing, and then you have this problem, and then say, so this is the main part. So you are taking A and B, and both are long variables. And just leave the fact that it is a Java program, because the core part of it, it doesn't really matter C or C++ or Java. This is the way to get input. Just like C out, you are just getting the next input. Okay, so next long, like that you are getting. Okay, from the input. So that's all it is. So you have two long variables, A and B, so that now you can hold up to a value of size 10 power 18. Okay, integer cannot hold such a big value. Okay, so what you are going to do, you are going to do something in the loop forever, and then you will break out. Okay, whenever. Okay, so if A equal to 0 and B, or B equal to 0, then you are exiting. If A is greater than or equal to 2 into B, then you will subtract A minus 2 into B. Otherwise, you will do B minus 2 into A, and then you will break. Okay, so or nothing of it, then you will kind of break, and then you will output A and B. Okay, so this is the end of the process. This is until when the process is fully functional. Okay, so when you run this particular program, you will get what is called as a time limit exceeded error. Okay, so if you look at this, it said the time limit exceeded on test 3. Okay, so let me pull out the test cases. And if you look at it, the first case answer was correct, second case answer was correct, because these are all sample. The test case 3, if you look at it, they are given a very huge number, and A to be very huge number, and B to be very small number. Okay. The idea is now you will reduce this number minus 2 into 7. Okay. That number is even bigger. So again, minus 2 into 7, minus 2 into 7. You will keep doing it, and then that's the reason now it's getting time limit exceeded. Okay. Every time I'm reducing 2 into B, 2B, 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 minus 2B, minus 2B, minus 2B. I'm doing that. And because this is a very small number, B is very small number, and A is very large number. So it's going to take immense time for me to come to a point where either the condition, the one of the conditions matter, right? These conditions hold. So I'm going to get stuck in this forever. I'm going to keep doing it. Forever, I'm going to keep doing it. Okay, and now after a very long time, I'm going to get it. Okay, if A and B are not that much apart, then it's not a problem. But because A is really very huge, this is the problem that you're facing. Okay, now you need a better solution for it. So what you can do is, one fact that you can realize is, say if I am doing A minus 2B, then minus 2B, it becomes A minus 4B. Then again minus 2B, it becomes A minus 6B. So like this, I keep reducing, right? So instead of doing it bit by bit, what I can do is I can divide A by B and find out how many times what is the quotient. Okay, with that quotient I'll be able to manage it, right? So because ultimately that is the amount of B's you are actually subtracting from there. Okay, so that is the logic that we need to apply, and therefore we can. So this complexity will be very huge because you are doing subtraction. Okay, but if you do use a division method, you can get to there very fast, right? You can get to there very fast. So now let's look at that particular solution. Okay, so this is like an accepted solution. I can go into it. I can see that. So now what I do is I'm just checking whether if QA is greater than 1. Okay, and I'm just trying to get the remainder of A divided by B and B divided by A. Okay, and if it is if the if I can divide it with a if it's a even number of times that I can divide, then I know that 2A can be subtracted, right? 2A into Q, that many number of times I can subtract it, right? So therefore, I will reduce it to QA into B. Okay, this is once for all I'm doing, right? This is once for all. So therefore, I can do this much. Okay, instead of saying 2A, sorry, what was it? A minus 2 into B, A minus 2 into B, like that. I'm just saying A minus 2A into B. That's what I'm doing. So I'm able to do it at one shot. Okay. And then if not, if it is an odd number of division, then I will do this kind of an operation. Okay. So that means I will not be able to divide QA number of times, but I'll be able to divide Q uh, A minus 1, right? So that's what I have. So similar thing you have for B stuff. Therefore, what we have effectively done is, because of this QA, it's obtained using a division. Okay. Instead of doing multiple 2As, 2As, 2As like that, so you will get to the thing much faster. Okay. In fact, in one operation you will get to that. Okay. And then you can go and then repeat again this particular process. So this division actually is going to save our time. Okay. Now when I submit this, then it will say it is accepted. This is an accepted. Okay. So if you click here to see the test details, you have this. Okay. So this particular big number, it has passed. Because of the division method, it has passed. So that's basically the idea. And you can look at the so many number of test cases they are used to check. So imagine how many number of test cases are there. Look at it. Okay. You can scroll through it, but I'm saying about 81 test cases are there, given different kind of things. A and B are same. What will you do? Okay. And they have given a whole lot of stuff. You can check out on these things. Okay. So how the test cases are there. So basically, the bottom line is the time complexity matters. When you write an algorithm, make sure that your algorithm can be the most efficient one. Okay. Otherwise, even though your logic is correct, it's not going to accept it, and it's going to say time limit exceeded. Okay. So that is purely due to the time complexity. Okay. So time complexity really matters because that shows the efficiency of your code. Okay. So you need to make sure that your program is very time efficient. Okay. So that's basically the idea. So I would stop at this particular point. Okay. You can ask any questions or any doubts.
No, sir, we do not have any doubts from the students.
Okay.
Yeah, so I hope we can end the session. Thank you so much, sir. Thank you for a wonderful session. So we'll see you all next week.
Okay.
So till then, yeah, good night. Yeah, thank you all.